Hey guys, welcome back. In this video, we're going to talk about solubility, pH, and some fun things that go along with it. All right, and so pH affects the solubility of ionic compounds that contain ions that hydrolyze. All right, so what does this mean? All right, so the pH, of course, is the hydrogen ion concentration. Right, how much is there? Solubility, that's the molarity. Ionic compounds, right, are salts that contain high ions that hydrolyze or react with water. All right, so calcium carbonates are an example. All right, and so we would have CaCO3 solid. All right, and that is a sparingly soluble salt. You have calcium ion in solution, and you have carbonate. All right, and that has a KSP value. All right. Hydrolyzes, right? What hydrolyzes? Well, carbonate would. Calcium group 2 metal does not, but carbonate would. So CO3, 2 minus, plus H2O, you would get what on the other side? Well, carbonate is not a proton donor because it doesn't have a proton to donate. So you're going to make HCO3 minus bicarbonate, and then hydroxide. And that would be a Kb for carbonate. All right. And so now if we add those up, I would have CaCO3, calcium carbonate, solid, plus what? Water. Going to what? Calcium ion. And bicarbonate. And hydroxide. And this new K is KSP times the KB. All right. And so what happens? We're just going to look at a principal level. What happens is the pH, right? In this case, hydroxide is here, right? And so if the pH goes up, if the pH increases, right, that means there's more of this guy, more hydroxide. If there's more hydroxide, the reaction shifts left, if that makes sense. So even less calcium carbonate will dissolve. So if your water is basic, calcium carbonate is not dissolving much at all. However, if you add acid, so adding acid would be anything that's H3O plus. If you add acid, it's going to react with what species up here? Well, it's going to react with your base, which is OH minus. And that, of course, will make 2H2O. So if we were to add those two reactions up now, what's going to happen? Well, one of the waters is canceling, right? That water's gone, and just that. And the hydroxide then goes away, okay? So you'd have your CaCO3 solid, plus your hydronium now. You still get calcium ion. We would have bicarbonate still. And we'd have water. And this K now would be whatever KSP is times whatever KB is all over what? Well, the reaction right here is 1 over kW. And so, as you can see, the pH, if we had play with the pH in some things, right? Now, if we add here, right, okay, the reaction's going to go that way. So, the more acidic you get calcium carbonate, the more likely it is to dissolve. All right? Another example of this stuff. Magnesium hydroxide is only sparingly soluble in water, but its neutralization by a strong acid is complete. All right? Explain, why is this the case? What's going on here? All right? And so if we look, magnesium hydroxide, first of all, magnesium is Mg, 2 plus, hydroxide's OH minus. Strong acid, we're just going to put H3O plus. Let's just assume it's HCl. But we're going to just put HCO plus, H3O plus. It doesn't matter. All right, so magnesium hydroxide. Let's write the equation here. MgOH2, solid. And we get Mg2 plus 2OH minus. And that's KSP. And we have the number now. All right. To neutralize this, we have 2 hydroxides here, right? There are 2 hydroxides, so you would need to have 2 OH minus plus what? Well, it had to be 2 hydroniums. And that's going to give us what? Looks like 2 H2O. Right? And if you remember from above Kw, right, which is the concentration of hydronium, that's concentration of hydroxide, right? It comes from this reaction of H2O. 2 of them go into H3O plus and OH minus. Now, before I continue, can you see my mistake? I did a simple mistake. I'm glad I did it. Mistake, because I did the same mistake a lot of students have made. I have 2 hydroxides and 2 hydroniums. How many waters does that make? It's not 2 waters. Four waters. All right? Because if you do the number of oxygens, I have 4 oxygens on the left, so I need to have 4 oxygens on the right. So that mistake is very easy to do. Right? Now it's just going to make my balanced equation wrong, but that's okay. And so this reaction up here has this K value, right? We are inverting it, so it's 1 over K, and then there's 2, 1, 1. We have 2, 2, 4. So we got to square K. So this happens to be 1 over KW squared. Okay. So if we were to add these reactions up, what would we get? Well, we'd have our magnesium hydroxide plus 2 hydroniums, giving us what? Magnesium ion and 4 waters, I believe. So K would be equal to KSP over KW squared, which would be 1.5 times 10 to the negative 11th, all over 1.0 times 10 to the negative 14th squared. Well, you can just square that and bring it up, make it positive. I'm thinking we're getting 1.5 times 10 to the 17th, which is a large number. Means a reaction, right, goes, right, to completion, pretty much. Just a little bit doesn't dissolve. All right, for most part, it dissolves. So that's how an acid, right, makes this happen, right? Because we have this huge K now, all right? And so that means this reaction, because we add that acid, it'll react with this guy. It goes this way. So the more acid you add, the more it goes until it's completely gone. All right. So now, let's do a couple examples. Which of the following compounds are more soluble? So which of the following compounds are more soluble in acidic solution? Right? So if you're going to be more soluble in acidic solution, what do you have to have? So acidic solution, H3O plus, right? Proton donor. So we need to find proton acceptors. So the first compound, silver, Ag plus, cyanide, Cn minus. Silver cyanide, all right. Well, is silver going to be a proton donor? No, this is a Lewis acid. So silver is not going to be a proton donor or a proton acceptor. It's actually a Lewis acid. So cyanide, Cn minus. That going to be a proton donor? No, not a proton donor. What about a proton acceptor? Can we get plus H3O plus? Can we get HCN and OH minus? I think we can. Right? Because this is a weak base. Right? Because there's HCN. So I would say silver cyanide dissolves better in acidic solution than pure water, because cyanide's a base, it will react with the acid. Lead iodide, so Pb2 plus, I minus, right, for PbI2. So again, Lewis acid. I minus. Well, will I be a proton acceptor? Hi plus OH minus. This is a strong acid. So B does not react with an added acid, and so that's not going to happen. Well, I have a mistake here. Again, I'm doing this to you guys. This should be HOH. All right. C, aluminum. Aluminum hydroxide. All right. AlOH. Well, you have hydroxide, right? So, of course, that's going to react with an acid. So, of course, that one's going to happen. Right? Which makes sense. Okay? So, it's a base. Zinc sulfide, last one. Zn2 plus, S2 minus, ZnS. Again, zinc is a Lewis acid, right? Metal cation. S2 minus plus H3O plus. Will this work? Will this get HS minus and H2O? Well, yeah, this is a base. So D is also more soluble. All right, so what's not is the question. Well, I minus. So what are the ones that are not soluble? Right? Nitrate's one. Chloride, bromide, iodide, chlorate, and perchlorate. Do you recognize those? Hopefully you do, right? So those are our anions that come from strong acids. All right? Yeah, I guess the other one would be HSO4 minus, right? This is still a weak acid, but it's not going to accept a proton. It's not a base. So these are not bases. All right. Hopefully that works for this one. And we'll see you in the next video, guys. If you have any questions, reach out.